everybody. So we've got some reading things that I had you all do, and we'll get started with those. And then we'll talk about the two videos from fellow faculty members upstairs and give you a sense of what they do for research, as you all might be thinking about getting involved in that. I certainly encourage you all to get involved in research as early as possible. I do think it's one of the best learning experiences you'll ever have. Not just from the viewpoint that you can actually use that experience to build your resume. The lab is really where you learn chemistry. Any science, actually. You're going to learn that mostly in the lab. Very little of it will you actually learn in a classroom, believe it or not. Because, again, science is about a method more so than a collection of facts. And so when we're in class, we tend to talk about a collection of facts. But, you know, we want everybody to be practicing scientists, whether you end up being an actual professional scientist or just an informed citizen being able to dive into something and figure it out for yourself, so to speak. So the first thing that I wanted you all to read today was phlogiston. How many of you have heard of phlogiston before? Was this new to everybody? Okay, so there's a lot of history that we don't teach you all anymore, especially in science. We think we come in and we only do the modern stuff and we forget about the stuff from the past. Phlogiston is an interesting read. Now, of course, you just got one page there. What did you all take away from the reading? What was interesting to you about it? Yes, ma'am. Okay, yeah, it's talking about a hypothesis or a theory, right? That it ultimately ended up being proven wrong. What else do you all take from it? What struck you when you read it? Anything?
I just thought it was interesting how close they were to being right, but not really. You know, one or two pieces that didn't have access to.
That's right. How do you all imagine that the phlogiston theory, we'll call it, come about?
Why does fire get suffocated?
Okay, so I mean it was an observation of fire, right? Humankind discovered fire somehow. I don't know all the history to that. I'm sure somebody probably knows more about that than I do. But imagine several thousand years ago being somewhere and finding something burning, and you realize that it's giving off heat, right? And you realize that it has potential utility, right? You've discovered you could cook your food, you can stay warm in the winter. Won't you start being curious about what this thing that they started calling fire was, right? What is it, right? Why is it that when lightning strikes a dry patch of grass or whatever the case may be, it bursts into flames, right? Humans really want to discover why on a lot of things, even though science doesn't ever answer the question why. It answers the question how, right? But nonetheless, humans will sit there and go, I wonder why that is the way that it is, right? And so what did they think? So tell me a little bit about this phlogiston, right? So we have an observation, fire and heat and all this stuff. They come up with this concept of phlogiston. What did they think phlogiston was?
Something fire gives off.
That's right. So it's something that a material contains and during the process of burning it gives off. And what kind of observations did they make about phlogiston? It usually gets what?
Lighter.
Lighter? In terms of mass? Mm-hmm. Yeah, right. So typically things lose mass, right? Right? If you burn paper or wood, right, you end up with just a small amount of ash, right? And so they felt like that became lighter, right? Is that true? For many things, it seems to be true. When you don't take into account the fact that you release carbon dioxide. They knew nothing about carbon dioxide yet, right? They didn't even know about oxygen yet, right? But they knew that if I took a block of wood and it had a certain size dimension and it weighed a certain amount and we lit it on fire, it gave off this heat. That heat must be phlogiston, and what was left was the mass of the material minus its phlogiston that was given off, right? What else did they observe about quote-unquote phlogiston?
When you try to close the fire, it's suffocated.
Okay, yeah, so if I've got a fire, let's say we got a candle and I put a jar over it, the fire goes out, right? They made that observation. And so what was their rationale there?
It was put out by the phlogiston.
Yeah, they said, well, apparently air can only hold so much phlogiston, right? And so once it's saturated with phlogiston, it goes out. Notice they kept trying to bend their theory to fit whatever the observation was, right? But there were some observations about certain things that burned that were anti to what most things happen, right? And that were the metals. When you burn them, they noticed when you burned a metal, it gave off heat, but it gained in mass, right? And so that seems to disprove the phlogiston theory. Imagine trying to figure all of this out without the advent of modern technology, right? All you have are your eyes, your hands, your sense of smell. You might have a ruler. You might have a balance of some sort that you can weigh things with. But that's about it. And it's left up to you and your wits, so to speak, to try to figure out what's going on when you set something on fire. Okay? This is an excellent example of where people came up with these ideas and then the scientific method kicks in and you start to work on it. We very well could have decided to call oxygen phlogiston in the grand scheme of things. We didn't, right? But nonetheless, phlogiston today, we look at that and we read that and we go, how silly they must have been, right? To not know that wood or whatever we're burning has to have oxygen. You all, ever since you have been little, have been taught that combustion occurs because you have some fuel and some form of oxygen, right? They were not privy to any of that information that we're privy to today. Okay? So today's activity, we're going to break up into 5 groups, which is going to be, each row is going to be its own group, and you guys on the side are going to be your own group. Somebody in the group is going to be what I call the scribe. Right? So you're going to get a piece of paper, you're going to put everybody's name on it, and you all are going to do some things. I'm going to pass out some boxes. And these boxes are grayed out, so you can't see what's inside. Okay? So the box itself actually represents what we can physically see in the universe. Okay? Fire, if you will. Okay? Okay, the box can be opened, but you cannot open it. Okay? And you're going to sit there and you're going to make some observations. You're going to propose a hypothesis about the box from your observations. You're going to come up with some theoretical tests that you might be able to do to try to determine the nature of what you're observing in the universe. And we're going to go from there. Okay? So, each group gets a box. Get together, decide who's going to be the scribe. The scribe's going to be used on your name and everything on the sheet. It's going to be what is used to determine your attendance today. You can use anything at your disposal that you have right now, just like they did hundreds of years ago, except you can't open the box. So the scribe needs to put down the observations, any hypotheses that you form, what tests you might use to address those hypotheses.
I want to actually use those. We've got like markers.
So they had like sides to it.
Yeah.
Yeah.
You can hear them turn
It's like a bunch of you can say the solid size.
Oh, yeah.
Yeah, you can't really double the like that.
If like a nearsighted guys, it would be just lighting.
More dangerous.
Something weird like that.
I want you to see what
I thought it was like not dies.
Yeah. I feel like you can hear it when it's not something.
Yeah. And normally that's not what it just do it side to side and just slides. Like this is like turning, but it's turning.
Exactly.
You just have all these like back.
I'm gonna give you about 4 or 5 more minutes, so observations, some sort of hypothesis and how you might test that hypothesis. And you have all that on your sheet.
It actually seems kind of like, I don't know, whatever it is, this side is not
I couldn't figure out how to say it. Alright.
Or is that just it?
No, there's.
Yeah.
I know what I put in all the boxes, yes, but I don't know which box you have. I don't even know which box you have. Pardon?
Perhaps. That you figure out.
And not what that means.
Well, we're already, yeah, we're already through it. Okay, so we have the hypothesis is so the way we say it is if it makes use as a market and makes noise, then it's possible to run. How are we testing it? It makes. So we would.
It's an
A statement of what we do.
So like
And it's set up several similar boxes with different materials. I feel like it's on the
We could weigh and empty. I feel like it's consistently turning, so it has to be how much you do subtraction to figure out what the weight is. We don't know all these.
I'm gonna just 2.8 and then I say then it is
One more minute.
Alright, Jeremy. Here. Observe box. This is it.
Okay. Stay in your groups. And let's let me borrow this one for a second. We're not going to open them yet. We're going to have a little discussion. Let's think of this as the fire, right, for the phlogiston theory, right? This is what we can observe, right? What did you observe? It's a solid. What else did you observe? It's what? Pieces of metal. Does everybody think they have pieces of metal inside?
Just multiple solids inside.
Something's inside, right? Something or some things?
Something.
Something. Yeah. Some things. Depends, right? How are you observing the box? Largely you're shaking it, right? How else could we have observed the box? Huh? Roll it around, right? Yeah. We could have measured the box, right? Many of you probably don't have a ruler, but you could have used your phone or something else. You could have used a piece of paper and you could have said, it's about a quarter of a sheet of paper, that's about whatever. You could have come up with some rough dimensions of the box. What other visual cues did you come up with the box? Anything? Yeah, I think we pretty well covered it. You might have thought, I wonder how dense it is. I heard somebody talk about density earlier, right? How could you have determined the density of this? You'd had to have figured out the volume and the mass, right? And then you would have done the division. You could have also, put it in a tub of water to see if it floats or sinks. All right, that would tell you whether or not it has a density greater than or less than water, right? Which would have given you something about the internal workings of this, right? Is it a solid box? Or is it a hollow box? It's a hollow box, right? You all know that because you hear something moving around in there, right? You could have listened to about how much time does it take for it to go from one end to the other, right? That could have given you some idea of the size of the thing in there, right? If it went from one side to the other real quick, maybe it's long, right? If it seems like it takes a little longer to get over there, we could have. Could you have determined the mass of what's in there? Would have been difficult, right? But think about it for a moment. If we could have suspended the box to where it's perfectly balanced, and then we tilted it to where the mass on the inside is on one side, we could have counteracted that with masses on the other till it balances back out again. You could have made a crude balance. Now, you probably wouldn't have been able to do it very accurately, but you might have put pennies on one side or whatever, and you said, well, whatever's in there must weigh about the same as 2 or 3 pennies, right? But you're limited into what you can actually see inside this box. Today, in science, we can see inside the box a lot easier than they could have back in the 1600s. We have a lot of instrumentation that allows us to see inside the box. So now, if you think about modern day kinds of things, what could you have done to the box to try to see what's inside of it? No, can't open it. Still can't open the box. A good try. Could have taken it to the doctor's office and had him do an x-ray. Right? We can see inside boxes now that we couldn't have seen back in 1667. You could have shown a very bright light on it, maybe thinking that you could have penetrated the box with some really intense light and saw what the shadow was on the other side. Right? We do things like that all of the time. How else could we have interrogated it? I heard somebody over here talk about using something else, putting up towards it. Put a magnet up against it, right? We could have interrogated it with a magnetic field, right? You all think you have something that's metal in the box, right? That would have made sense. It moves around. Well, if I put a magnet on it, does it move around anymore? Right? We could have interrogated the box an awful lot, actually, right? So what kind of test did you all come up with to test your hypotheses? Well, let me ask this first. What do you all think is in the box? What do you all think is in there?
Dice.
You think dice are in that box. What do you all think is in the
I
box?
think like rocks or beads.
Rocks or beads. What do you all think is in the box? A magnet? Okay. What do you all think is in your box? Pardon? Beads. And what do you all think is in your box?
I'm not exactly sure, but it sounds part metal, part plastic.
Okay. You think it's part metal, part plastic? What about the number of items inside your box? Does everybody have the same number of items? How many people think you have one thing in the box? How many people think they have multiple things in the box? The rest of you, right? Do you have any idea about how many are in the box? If you were to take an educated guess, what might you all say? More than a dozen?
That's not me,
That's not me. You're not building consensus on that, okay. How many items do you all think you have in the box? 4 or 5. Why is it that you all think you have one item in the box?
I don't hear anything else. I mean, I hear like maybe something attached to something bigger, but.
Oh, okay. Well, now through the magic of modern science, you get to open the box and peek in. All right? So go ahead and open your box, lift the lid, don't spill anything, and peek in and now make an observation of what you see. Okay, now I want everybody to see what everybody's got, so we'll start up here. You all show them what you got in the box. You got 3 like marble glass stones is basically what you have. I took those out of my wife's flower arrangement. What do you all have in the box?
We have 4 tiny dice.
4 tiny dice. What do you all have in the box?
A washer and screw.
Can you show it? Where's that? Yeah, so you got a washer, a nut, and a bolt, right?
That was the first thing she ended up saying. Like that was like the first thing she
Really?
said.
Now you said that you thought that there was more than one thing connected together. What led you down that path?
Well, I didn't feel 2 things, the masses moving around on different sides, and then the washer, I don't know, it's just a thin piece of metal that I felt like would be attached to something else.
You could hear like 2
Yeah.
different sounds
Yeah.
that it was making.
Okay, so you were tuning into how things sounded, right? You were trying to compare it to your known. What did you all have in the box?
Popcorn kernels?
Popcorn kernels. How many do you have in there?
14.
13, 14. You all thought there was probably about a dozen things in there, right? You thought there might be a dozen things in there, but you didn't think that it was going to be popcorn kernels, right? What did you all have? 4 screws, right? That were metal. Okay? So go ahead and close the box back up. Now that you know what's in there, revise what you might have wished you would have had the access to determine. In other words, what tool or technique might you have wanted without being able to open the box to try to determine it?
Yeah.
Ours is still working.
Yours still works, the manual will help.
Oh, it's popcorn.
The magnet just lets me know
You all could have put it in the microwave. Right, so.
Had we done that though?
Oh, that was.
Yeah.
What is it like?
Okay. Take just one more minute to finish up your writing. And then we'll carry on. Okay. Has anybody ever done that type of exercise before? You have? Where did you do that at?
My colloquium class.
Pardon?
My colloquium class for honors.
Okay. Colloquium class for honors. I did this when I was in high school. We actually used shoe boxes, though. It's a way of scaling up how science occurs when you have limited knowledge, right? You start from some observation. You all formed hypotheses. Some of you were very close, at least in pieces of it, right? Well, we think we have a dozen, but you ended up having 13 or 14. Well, you know something's inside the box, right? And you know about how much is there. You're right with that, but you didn't know it was popcorn kernels yet, right? So you would have then interrogated it further. You would have done something as tools come along. You would have looked at it more closely, etc. For those of you who had metal things, you could have used a magnet, right? For you all, you would have been able probably to determine that it's a single unit of something that's metal. The folks on the left over here, you probably wouldn't have been able to determine the number from the magnet, right? It would have probably pulled them all together, but nonetheless, you would have been able to get down to that. You all thought you had dice, but the people behind you actually had the dice, right? But they had similar probably characteristics in terms of that box, right? So the whole point of that exercise is to let you know that the scientific method is iterative. Right? You make an observation, you form a hypothesis, you test that hypothesis with what you have. You come up with the best explanation you can at the time. Phlogiston worked for the most part until people started to burn metals. Wait a second, if we take some iron and we set it on fire, and you can do that, it gets heavier, it doesn't get lighter. That was enough to disprove the phlogiston theory, wasn't it? Right? For those of you with metal things, if you had said, I think it's metal, and you put a magnet to it and then you turn it, would that have disproven that it was metal? Are all metals magnetic? No, right? It could have disproven whether or not it was a piece of ferromagnetic metal, but I could have put a piece of copper in there. Copper's not magnetic, right? So you would have had to interrogate a little further. So a fun little exercise. I hope you enjoyed it. Anytime you start going into the lab to do real research, you're going to be in your own little world of phlogiston. When you go into the academic lab where we are teaching you techniques, you are not going into the world of phlogiston. We largely know what the outcome is in those laboratories. We're teaching you a technique. We're teaching you how to use a burette properly. We're teaching you how to use a piece of glassware properly. We're teaching you how to make observations. But your TA knows the outcome of that reaction or that particular experiment. And when you don't get it to work, chances are it's your technique. And you learn from that and you move on, right? But when you go into the research lab, which we're going to talk about a couple of people's research here in a minute, you know as much about the final result as your PI does, and that is nothing. They have more foundational knowledge, they have more experience, they have more ideas of where it might lead, But they don't. That's why it's called research. Nobody knows exactly what the outcome is going to be, right? And so you will be in a world of quote-unquote phlogiston during that time. You will be interrogating. You'll be examining. If you really enjoy that kind of thing, those types of puzzles, research is for you. It may not be what you do for a living, right? But it is something that I suggest you get involved with. If you really like that kind of thing, then chemistry research is going to be for you. Let's talk a little bit about Avogadro's hypothesis. Where have you heard about Avogadro before? Avogadro's number. Avogadro's number is what?
6.022 times 10 to the
23rd, right? 6.022 times 10 to the 23rd. 10 to the 23rd what?
mole.
It tells you how much stuff is in a mole, right? And a mole is just a way in which we count very, very large things, very, very large numbers, right? So if you think about 6.022 times 10 to the 23rd, that's a really big number, right? It's 23 zeros, right? It is so large that it kind of baffles the mind, right? But what do you all know that has 6.022 times 10 to the 23rd in it? One mole has that, right? So let's think about that number for just a second. How much volume of water would you have to have 6.022 times 10 to the 23rd molecules of water?
33.01 milliliters.
Okay. So how do we figure that out? Right? We know the molecular weight of water is 18, right? Oxygen is 16, hydrogen is 1 apiece.
Oh, never mind. I was doing 2 oxygens. Never mind.
You're doing hydrogen peroxide?
Yeah.
Yeah, okay.
So what?
Turns out it's 18 milliliters. Water weighs approximately 1 gram per milliliter, right? So you need 18 grams to have a mole, right? So 18 milliliters of water is 6.022 times 10 to the 23rd, right? You do not have 6.022 times 10 to the 23rd molecules of DNA. That would be a whole mole of DNA. DNA is a huge molecule. It would be more than your mass, right? You just don't have that much. But you've got many moles of water in your body, right? So yes, Avogadro's number, you all know that. But Avogadro's hypothesis really was that if I take different volumes of gases, or excuse me, different gases at the same volume, he said what? So I've got a balloon full of carbon dioxide, I've got the same balloon full of oxygen, I've got the same balloon full of hydrogen. Right. They will weigh differently, but they all have the same number of molecules. That was his hypothesis, right? And so he was getting to this idea of atomic mass, right? That yes, a volume of hydrogen and the same volume of oxygen, they will weigh different, but each one of those will have the same number of molecules, right? How much volume is a mole of a gas? Now, some of you may not have learned the ideal gas law yet. Has everybody learned the ideal gas law? If you have, that's good. If not, don't worry about it. You'll learn it. PV equals nRT, that's right. And you learned that at standard temperature and pressure, or you will learn, that at standard temperature and pressure, 1 mole of an ideal gas occupies 22.4 liters. 22.4 liters. That's roughly-ish the size of a regular trash bag. Okay, so you take a regular trash bag, you fill it full of gas, you'll approximately have a mole of air in it. Okay? When I was in high school, my chemistry teacher, unfortunately I didn't get to see this, but I heard about it. It happened the year before I took chemistry. somebody asked him, I wonder what it would be like if a mole of hydrogen gas was detonated. So they took a garbage bag that was approximately 22.4 liters in size, and they filled it with hydrogen gas, and it floated, and they took it outside and they lit it. In that process, that hydrogen gas was converted into water, heat, and a loud bang. That water that was made was only 18 milliliters in volume, if you could condense it all. But you had 22.4 liters of hydrogen gas that exploded. It made a boom. The principal was not happy when they did this. It really knocked some people back for a loop. Because a mole of hydrogen gas actually generates an awful lot of heat. Okay? But Avogadro's hypothesis really was instrumental to us in being able to determine this idea of molecular and atomic weights. It led us down that path. Okay, so very, very important. And it all started with gases. Why do you suppose he hypothesized that the gases would have the same number of molecules if they were at the same volume? Where do you think he pulled that from? Other scientists? Maybe. But I would wager if he got it from other scientists, we probably wouldn't call it Avogadro's hypothesis. Right? He probably came up with this. What observations might he have made about gases that led to that hypothesis? What do we know about gases? We know we can compress them, right? And so he probably made some observations that you can take any two gases that are different and you can probably compress them nearly the same, right? We know that pressure is the molecules pushing on the walls of their container, and he probably noticed that the pressures were kind of similar. And so he probably worked his way down the line of saying, well, if all of these things are about the same, then these gases in these volumes must be about the same amount of molecules or atoms, whatever the case may be, right? Probably led him down that type of a path. And so we ended up with Avogadro's hypothesis. We ended up with Avogadro's number. Avogadro's number is very, very useful, right? You use it all the time when you're solving chemistry problems. It is everybody's bane in a way, right? Because it's such a large number. Talk a little bit about the periodic table. Last year was really fun when we talked about the periodic table. I had a lot more stuff to show because last year was the International Year of the Periodic Table. According to IUPAC, I believe it was the 150th anniversary of the development of the periodic table. Why is the periodic table so important to you all?
You use it for like everything.
Almost. Right? Before the advent of smartphones, when I was in college, I actually made a copy of a periodic table, shrunk it and laminated it and put it in my wallet and carried it around. You might think that's kind of nerdy, but you can answer a lot of questions just by looking at the periodic table. What kind of questions might you be able to answer by looking at the periodic table? Charge, okay, might be able to figure out the charge of an atom. Okay, what else might you be able to figure out?
Atomic weight.
Atomic weights, all that information is on there, right? We know that oxygen is 15.9994, I think, right? Roughly 16. What else do we know? Electronegativity, right? We can start to see how atoms attract electrons to themselves within a bond, right? Pardon?
How many protons each
Okay, yeah, so you can tell how many protons there are, and if we know how many protons are in an atom, we know how many electrons are in an atom, right? So we know that atomic number tells us the number of protons, and we know that in a neutral atom, the electrons have to be equal, right? Okay, very good. So we know something about protons, we know something about electrons. Do we know anything about neutrons? Sure we do, right? Because we know about isotopes, right? We know that this atom has a certain mass. We know that the mass of an electron is essentially zero. It's not quite zero, but it's really close, right? And so we know that the difference has to be made up by neutrons. Yep.
The shape of their orbital.
You can know what orbitals the electrons are in. Yep. You can start to know something about chemical properties. Right? When I look at a periodic table and somebody asks me something about sulfur, for example, I know that sulfur sits right under oxygen, and I know a lot about oxygen, so I can infer that sulfur will have similar chemistry, right? So if I take oxygen and I do something with it, I can expect that sulfur might do something similar. Why do I say similar but not identical?
Because it's not the same element.
Yeah, sulfur's not oxygen, right? But it's in the same what? And what else do we call a group? A family, right? Things that are vertical in the periodic table are families. And remember that because families always stand together, right? So I know within a family I'm going to see similar but not identical behavior. What's the other way in which we think about the periodic table? Things moving left to right. We got rows and we've got periods, right? Or families and periods. And in a period, do we expect the chemistry to be the same as we move from left to right? No, but it moves in a predictable way. I know that as I go from left to right in the periodic table, I get more and more electronegative. So I know that the bonds are going to become more polar, right, for the most part. What else can we figure out from the periodic table? Yeah, we can figure out size. Yeah. You all, as majors, you should have an app on your phone for the periodic table these days, because you're going to be able to walk into a laboratory, somebody's going to ask you a question, and you're going to be able to get a lot of information from the periodic table. I used to have to pull that thing out, and I would look, and I would squint, and I would figure out. But if you have a really good app, you can also figure out what its crystal structure is, whether it's face cube or whatever. You can figure out roughly how many bonds that atom will form with other elements. You had a question. You had something you wanted to say.
Oh, I can't remember the word. Iso something.
Isotopes or isoforms?
I don't know. I forgot.
Okay. Yeah, but you can figure out a lot of stuff from the periodic table. Is the periodic table done? No. We think we have found everything that exists in nature, but we are making these so-called transuranium elements, right, that we make in a laboratory, okay? And they are important. Well, let me rephrase that. To most people, they're kind of exotic and eccentric folks in a nuclear lab trying to figure out how to make new elements, right? So they'll take a target element, they'll shoot neutrons at it, and they'll make new elements. Some of them are stable, some of them are not, okay? But this is important, especially for those of you who are going into medicine, okay? There are a number of man-made elements that are useful in the treatment of cancer, okay? How many people have heard of Oak Ridge National Laboratory? It's in Tennessee. It's a nuclear lab, right? They have been involved in, making atomic weaponry and that kind of stuff. But they also do things that are very related to medicine. They have this thing that they call the cow, believe it or not. They call it a cow, and they milk it, okay? Chemically milk it for its radioactive materials. And there's one element in there. I'm not going to tell you what it is. You all need to go look it up on periodic videos. There's this thing on YouTube called Periodic Videos, and there's the thing about the cow at Oak Ridge. They actually milk this thing periodically to get this one particular radioisotope that gets formed over time in the cow as things decay. So it literally is nuclear waste that they're extracting this stuff from to make anti-cancer drugs. And they ship this out all over the United States every year for use in oncology. Okay? But you won't be able to go out into a mine anywhere, in the United States and dig this element up. It just doesn't exist in nature. Okay? It exists from what happens when we make plutonium, and it's a side product, and it has all this use. So we spend billions of dollars a year, maintaining some of these national labs, and a lot of times people say, why are we investing this money in there? That's the only place that you're going to be able to get that kind of stuff. So if you have to undergo that type of cancer treatment, it's going to be really important to you. So the periodic table is definitely one of the things that you need to know a little history about. And so the fact that there was the International Year of the Periodic Table last year, there's a lot of nice stuff out on the internet, on YouTube, talking about the history of the periodic table. Interesting to me was like technetium. If you look at that on the periodic table, when they were putting the periodic table together, they noticed a hole. They found all these elements, and then they said, well, there shouldn't be a hole in our periodic table. There should be something that's there. And it turns out that it's an element that doesn't exist in nature to any great appreciation. You have to synthesize it. Okay? And I always found that kind of interesting. So you watched videos from two fellow faculty members upstairs, so to speak. This one was recorded last year from Dr. Julie Pigza. She is an associate professor of organic chemistry, so she and I are colleagues in that regard. I'm an organic chemist, as you know. What is an organic chemist? Somebody who works with carbon, right? But there's a lot of ways to work with carbon, right? We talked about chirality, right? And one of the things that she works with is this idea of making chiral molecules as well, using these catalysts. We've also learned a little bit about catalysts in here as well, right? We've talked a little bit about those. And so this just kind of gives you an overview of the things that she does in her laboratory. Okay? So if you're interested in making things, building things, working with Tinker Toys, Legos, this is kind of the chemistry equivalent of playing with Legos. Taking carbon building blocks and making new molecules for a variety of reasons. Now her group also works very closely with Dr. Jacques Kessel in biochemistry to make HIV integrase inhibitors, and that's one of the things that you see listed here as well. Okay? HIV integrase is an enzyme that is responsible for HIVs being able to be propagated within the human body. That's my limited understanding of it. And you want to be able to inhibit that enzyme to try to come up with not necessarily a cure, but a treatment for HIV. And it turns out that in the Deep South, HIV is actually quite, based on our population, we have a high incidence of HIV infections in the United States and in the Deep South. And so it's nice to see this type of research being done in an area that could benefit from that type of research, right? So Dr. Kessel focuses on the biochemistry of it. Dr. Pigza focuses on making the molecules that might inhibit that process from occurring. So does anybody have anything that they took away from the video that they found interesting? You want to share? Yeah.
I remember, she was like, it's important to make molecules that are the same, but different and have no chirality.
Mm-hmm.
But she didn't say that word. So I was like, oh, I know what that is.
Yeah, you already know what that is, right? What does she prefer students have before they come and work for her in her lab? Anybody remember what she said there?
She'd rather them already have taken organic.
Yeah, she would really rather you have already had at least organic 1, if I remember correctly. And that's because going into that, you're going to need to know some basic just nomenclature, think how we talk, right? So that you're not overly confused about different things. But, you can take organic in your sophomore year. You could actually start getting involved in her research group. Many of you now, I know some of you have already had organic. And for those of you who have not, next fall might be when you have taken Organic 1. So, spring of 23, you might be able to be in her lab working on some of this stuff with her. What I will say is she is funded by the National Science Foundation. She has what's called an NSF Career Award, which is the premier award for early investigators. And so she has ample funding to make sure that your research, you have everything you need to do. So I would highly recommend that you go up and talk with her. Her office is in 433, so if you go straight up to the 4th floor, kind of back off that way a little bit, you will find her office. You can drop by, talk with her, get to know her, and see whether or not you might want to join her research group. The last video that I had you watch was Dr. Carl Wallace. So he's interested in inorganic and supramolecular chemistry. What does that mean? Let's focus on inorganic first. What does inorganic mean? That's right. We're talking about things other than carbon, right? So he and I have a kind of a joke with one another. I tell him that the entire periodic table exists just to make a special place for carbon. And he says, no, there's so much more to study than just carbon. But nonetheless, even though he's an inorganic chemist by training, they do some organic chemistry as well. You have to make things. And he's interested in this idea of supramolecular chemistry. Does anybody know what that means? Well, usually they are fairly large, okay, but they don't have to be. Supramolecular chemistry is really about non-covalent interactions. You think about bonds, right? You have covalent bonds, and those are really strong. But molecules actually interact with one another more than just through covalent bonds. And that's really what he's interested in. Hydrogen bonding. You all have probably learned about that, right? Have you ever wondered how a sheet of saran wrap, when you fold it together, sticks? And yet you feel it and you're like, there's nothing sticky on there? That's supramolecular chemistry. Okay? It's nothing more than van der Waals interactions. How does a gecko climb up the wall? Right? Supramolecular chemistry is how that happens. Okay? It's these non-covalent interactions that allow your bowl that's covered with saran wrap not to leak and all of that kind of stuff. Now he uses this stuff to determine pollutants, for example. So he will be able to detect things in wastewaters or other things, either looking at things that are environmentally hazardous like cadmium, mercury, and lead, or industrial contaminants such as nitrate, sulfate, and phosphate. Ways in which you can put an indicator in there, if you will, and then see a response. That's really what he's interested in. So a lot of people really like to go and work with Dr. Wallace for a couple of reasons. One, everybody can understand the need to detect things that are hazardous in the environment. Number two, he doesn't do hardcore organic chemistry. It's very straightforward and simple. But three, it also has an analytical component to it. And a lot of people like analytical. They like to measure things because they see the immediate importance of doing so. So Dr. Wallace's work is really in that. Now you can find him on the 4th floor as well. I'm trying to remember his office number. But you can certainly go up there and talk to him and get involved in research in his lab. He has had several students who have applied for and gotten the Goldwater Fellowship over the years, so he works very closely with his students on that type of stuff as well. All right, so we've got 5 minutes left. I think we're going to be done for the day. So on your way out, please leave your sheet so I know to give everybody their attendance. And I will see you all next week.